Hello everyone and welcome back. In the previous lecture, we explored several important aspects of vibrational spectroscopy. First, we learned how molecules absorb infrared radiation and transition between tip vibrational energy state. Then we looked at different types of molecular vibrations such as stretching and bending motions. After that, we studied functional group absorptions and saw how specific molecule groups produce characteristic peaks in an IR spectrum. But an important question still remains. Why do these bonds absorb at those particular frequencies? Why does a carbon-hydrogen bonds absorb near 3000 centimeter inverse while a carbonyl bond absorbs near 1700 centimeter inverse? Today we are going to answer that question, and to do that we will combine chemistry, physics and classical mechanics. To understand vibrational frequency, we must imagine a chemical bond in a slight different way. Instead of thinking about atoms connected by electron clouds, imagine something much simpler. Imagine two solid masses connected by a spring. This may seem like an oversimplification, but surprisingly, it works extremely well. In this model, the two atoms behave like masses and the chemical bond behaves like a spring connecting them. When the atom vibrates, the spring stretches and compresses. This is essentially a harmonic oscillator, a concept we know well from classical mechanics. Because the bond behaves like a spring, its vibration follows Hooke's law. Hooke's law describes the restoring force in a spring system, and from its principle, we can derive an equation for the vibrational frequency of a diatomic molecule. The frequency of vibration is proportional to the square root of the force constant divided by the reduced mass. Mathematically, we can write it as shown in the slide. Now, let us carefully understand what these variables represent. The first variable is K, that is the force constant. In chemical terms, this represents the bond strength. A larger value of K means the bond is stiffer and stronger. A smaller value of K means the bond is weaker and more flexible. The second variable is mu, called the reduced mass. The reduced mass depends on the masses of the two atoms involved in the bond. It is mathematically calculated using the formula mu is equal to m1 into m2 divided by, in the bracket, m1 plus m2, where m1 and m2 represent the masses of the two atoms. The reduced mass essentially describes how heavy the vibrating system is. So now we have a very powerful equation, and from this equation we can extract two extremely important rules that explain infrared absorption trends. Let us look at them one by one. Rule 1. The first rule is related to the bond strength. If the force constant K increases, the vibrational frequency increases. This means stronger bonds vibrate at higher frequencies, and since wave number is directly proportional to frequency, stronger bonds appear at higher wave numbers in an IR spectrum. This explains a very common pattern we see in infrared spectroscopy. Triple bonds are the strongest, double bonds are the moderately strong, single bonds are the weakest. Therefore, triple bonds absorb at the higher frequencies Double bonds absorb at the intermediate frequencies and single bonds absorb at lower frequencies. For example, carbon single bond carbon typically absorbs near 1200 centimeter inverse. Carbon double bond carbon absorbs around 1650 centimeter inverse. Carbon triple bond carbon absorbs even higher, around 2100 centimeter inverse. The stronger the bond, higher the frequency of vibration. Now let us examine the second rule. This rule involves the reduced mass mu. Notice that mu appears in the denominator of the equation. That means the reduced mass increases, the vibrational frequency decreases. So the second rule is heavier atoms vibrate more slowly, therefore absorb at lower frequencies. Think about a physical analogy. Imagine two systems with identical springs. In one system, the masses are very light. In the other systems, the masses are very heavy. Which one will vibrate faster? The lighter system will vibrate more rapidly. The heavier system will move more slowly. The same principle applies to chemical bonds. For example, a carbon-hydrogen bonds involves a very light hydrogen atom because hydrogen is so light, carbon-hydrogen vibrations occur at frequencies typically near 3000 centimeter inverse. But if hydrogen is replaced by a heavier atom such as chlorine or bromine, the vibration slows down. As a result, carbon bond chlorine and carbon bond bromine bonds appear at much lower wave numbers. Now let us examine some real experimental data to see how these rules apply in practice. First, look at the carbon-hydrogen stretching frequencies based on hybridization. Hybridization affects bond strength and bond length. In sp3 hybridized carbon-hydrogen bond, which is typically in alkanes, absorbs around 2900 centimeter inverse. Now consider an sp2 hybridized carbon-hydrogen bond which appears in alkenes. The sp2 orbital contains more s character, making the bond shorter and stronger. Because the bond is stronger, the absorption shifts to a higher frequency around 3100 centimeter inverse. Finally, look at the sp hybridized carbon hydrogen bond found in alkynes. This bond contains even more S character. It is even shorter and stronger, and therefore its vibrational frequency increases further, appearing near 3300 centimeter inverse. This is a perfect example of how bond strength influences IR absorption frequency. Now let us examine the effect of bond order. The bond order refers to the number of shared electron pairs between atoms. A single bond has a bond order 1, a double bond has a bond order 2, a triple bond has a bond order 3. As bond order increases, bond strength increases. And according to Hooke's law, stronger bonds vibrate at higher frequencies. So we observe the following trend. Carbon single bond carbon lower frequency, carbon double bond carbon higher frequency, and carbon triple bond carbon even higher frequency. A carbon double bond typically absorbs around 1650 centimeter inverse, but a carbon triple bond carbon absorbs around 2100 centimeter inverse. And again, this follows directly from the force constant relationship. Now let us explore another important factor, that is resonance. Resonance occurs when electrons are delocalized across multiple atoms. This electron delocalization changes the effective bond order. Consider a typical carbonyl group, carbon double bond oxygen. In a normal isolated carbonyl group, the absorption appears near 1715 cm inverse. But if the carbonyl group is conjugated with a double bond, resonance occurs. The electrons become delocalized across the system. This reduces the pure double bond character of the carbonyl bond. In other words, the bond becomes slightly weaker, and when the bond becomes weaker, the force constant decreases. According to Hooke's law, that leads to a lower vibrational frequency. As a result, absorption shifts toward downward to approximately 1675 centimeter inverse. Why this matters? Because this understanding is extremely powerful. Instead of memorizing dozens of higher absorption values from a table, we can predict them logically by considering bond strength, atomic mass, hybridization, bond order, resonance effect, etc. We can estimate where a vibration should appear in an IR spectrum. This transforms infrared spectroscopy from a memorization exercise into a conceptual problem solving tool. It allows chemists and physicists to interpret spectra more intelligently and confidently. Let us summarize today's key ideas. We modeled a diatomic molecule as a mass spring system. Using Hooke's law, we derived a relationship between vibrational frequency, bond strength, and atomic mass. From this relationship, we established two important rules. Stronger bonds vibrate at higher frequencies, heavier atoms vibrate at lower frequencies. We then applied these principles to real examples involving hybridization effect, bond order trends, and resonance effects. These concepts help us understand and predict infrared absorption trends in molecules. Infrared spectroscopy becomes far more powerful when we connect it to the underlying physics of molecular vibration. By understanding the role of bond strength and atomic mass, we gain the ability to interpret spectra with logic rather than memorization. In the next lecture, we will continue expanding our understanding of vibrational spectroscopy by exploring normal modes of vibration in polyatomic molecules. Thank you for your attention. I will see you in the next lecture.